In case if you miss something, we can always come back. And I'm going to share screen. Okay, so today we're going to do basic time series analysis. And you have your data already downloaded. So we're going to pull it up and work with that data. Uh, so the first thing we do is go to File, Import, because this is not Stata yet. This is Excel. So import Excel, browse to find where you downloaded the file. So ours is here. Gold soy T-bond. It's going to give you a preview down here. Notice that the variable names are on the first row. So we're going to specify to import first row as variable names. Okay, so that you have the right format. Okay, variable case, let's make it all lowercase to save time. And okay, import. Okay, now if the letters are black, uh, then we're okay. So then we go to take a look at the data. On the top here, click on the icon that has the data table looking appearance. On the left one with the pencil, that's the one where you can change data. So we're going to go to the one with the magnifying glass so that you're just looking at the data. Okay, do we have everything? Looks right, right? The first row is missing for gold and soybean, and then everything is here. Notice something that for missing data, it has to show as a dot for Stata to read that as missing. Okay, so we have everything here. Now we're going to analyze one variable at a time. Let's look at gold first. I'm interested in gold. What has gold been doing the last 5 years? Right? So we're going to create a variable that we're going to call it a time variable. Okay. So generate t equals underscore n. Underscore n just tells you the order of that observation. Okay. And that order of observation is going to be called t here. All right, let's take a look. Do we have it here? T, right? 1, 2, 3, 4. Perfect. Okay. The dates, we can take a look at those later, but the red, when they are red, we can't work with those. Okay. So far, so good. Now we're going to work with time series. So we're going to declare this data set time series. Statistics, time series, setup and utilities, declare data set to be time series. Time variable, t. Okay. And I don't know if this is going to make a difference. Format of the time series. Let's try weekly because our data is weekly. Go from there. Okay. I don't know, somehow it automatically says 1960 as the first date. I don't know why, but let's not worry about that. So T is set as weekly here. Now, once we declare the data set to be time series, we can work with it more easily. Graphs, line plots. We're going to create a time series plot. Type is line. And we want to plot gold price. Wait for it to plot. Okay, so that's our, you know what? Let me redo the whole thing because this labeling is going to be misleading. Okay, so that's the time series plot. Let me redo the whole thing. Take out the weekly part, TS set, and then two-way. Okay, so we have our data. These are the weeks, 250 weeks here. Okay, so that's our data. Now, of course, you can do easier. You can just say TS line, gold close. That's the same thing, right? Okay, so we can take a look and see what our data looks like. Now, does this look stationary or non-stationary? Well, you might think over here, pretty stationary, right? But once you get to what date is this? I don't remember. I think so. 50 is the first year, second year, third year. And once we get to the fourth year, it starts climbing up. Okay, so if we test only a certain part, it's going to be stationary. But if we, test a different part, it's going to be different. Okay, so let me clear the annotation here. Okay, and clear the annotate. All right, now let's do TS line. Uh, what's the other one? Soy. Looks like that during the same period. Now, if we look at the actual data points, you see that the gold price and soy, the range is comparable. We can actually put them in the same graph, right? There's no reason for it to be that way, but in this case, we don't have to scale the variables. We can plot them in the same graph and see what's going on. Okay, so let's do that. Let's TS line the whole, both variables together. TS line, soy, gold. Okay, what do you see here? Let me pause the recording. The soy price predict gold price. We run a regression, right? Gold as the dependent variable and soy as the independent variable. Let's see what we get. Okay, so if you run this linear regression, we're going to conclude that as soy price goes up 1 unit, gold price goes down negative, goes down 1.1 units. Look at the p-value, highly significant, right? But this relationship, you know what, let me try something else too. Because soy price today is not going to help us learn about gold price tomorrow. So let's try soy price last period. Does soy price last week predict gold price now this week? We can do the operator called the lag operator, L dot soy. So this is going to give us the soy price previous week. Yeah. Okay, so we look at the result here. What do we get? Similar number, negative 1.1. So soy price last week goes up 1 unit. Gold price goes down 1.1 unit. So if we have soy price today, we can predict gold price next week, right? Of course, if this is a good model and we can predict the gold price next week, we know what to do, right? If we know soy price this week, we can predict gold price next week and we can profit from it, right? And of course, you have to build a good model to do that, right? So this is called a distributed lag model. We have gold predicted by soy price, right? Or you could do gold predicted by gold price. Okay, gold price goes up last week. We expect to go up the next week. Now, of course, how many lags we use, that's going to be another thing we will do next. Okay, but today I'm going to give you the stationarity part. All right, so we have our gold, we have our soy. Let's test for stationarity. Let me, how do we test for that? So the product we want, now we want to test something like this. So as you can see here, the way we do that is just type in D Fuller and the variable. Okay. So let's test the stationarity of gold price. Okay. P-value 0.999. So if we say that gold is stationary, we'll be 99% of the time wrong. Right? So the test statistic 2.48, the lowest critical value is 2.57. So yeah, highly non-stationary. Now let me try something here. Notice that in this case, I restrict my sample to only week 150 and before. What do you see? Right? The p-value dropped significantly, right? Went from 0.999 to 11661. So stationarity, depends on the range of the data as well. If our range is stationary, we can work with that, even though the entire data set tells you that the data is not stationary. If the relevant range is stationary, we're okay. So in this case, from week 150 and lower, we're not that non-stationary. Let's try 100. Okay. Right. So if we work with data, so t less than 100 here, if we work with data for only 100 weeks, gold is stationary, right? So stationarity is not something that's inherent to the variable itself. It's just the nature of the time movement. In this case, if we focus on for the first 100 weeks, we have stationary data, right? Let's try soybean. Right? So the p-value 0.04, right? It passes a significance test at the 5% level. Now let's try soy, but soy is not stationary, right? So uh, that means that it's very likely that our regression result in the beginning here, because gold and soy, even though gold is stationary from week 0 to week 100, but soy is non-stationary in the same um, period, right? it might give you a spurious result. So in this case, notice something here. If we run a linear regression of gold on soy for a week less than 100, our result changed quite a bit, right? From week 0 to 100, the relationship is not there, right? But from week 100 forward, the relationship is strong, right? But that's not the true relationship, right? At least we can't be sure yet, because what we notice here is from week 100 on, you see the two variables moving in opposite direction, but we don't know why. We don't have any reason to believe that soy is causing the movement in gold here, theoretically. But they do move that way, right? That's the point about spurious regression. Two variables may have time trends that are different or that are the same. It's going to lead us to conclude that they're related, even when they're really not. Okay, so we have done the Dickey-Fuller annotate test. Okay, next we're going to estimate the uh, AR model for gold price, right? So to do that, the first thing we do is to select the lag order, right? Now, if you take a look here, right, AR looks like this, right? I mentioned that, the number of lags is based on statistics, right? So what we're going to do is to choose the number of lags that's appropriate, okay? So we're going to try this one. We're going to type in this command, varsoc gold, enter, okay? And it's going to give you this table, and it's going to give you different criteria or test statistics that we're going to use as your criteria, right? And then the corresponding number of lags is going to be here, right? The most common is AIC and BIC, as the selection criteria. So the one with the asterisk is the one that criteria chooses. If you use AIC, two lags. Okay? If you use SBIC, one lag, right? Or if you use other criteria, FPE, HQIC, so it's going to be different here. So it's either two lags or one lag, right? So let's say in this case we go with AIC, right? So the command we're going to use is actually ARDL, but we're not going to put the DL part. ARDL gold, and we're going to specify that AIC criteria is used. Okay, enter. Right? So that's our result. Lag 1 coefficient p-value, lag 2 coefficient p-value. So lag 2 is actually not that strong predictor. Okay. So the two steps here, varsoc and ARDL. Okay, let me pause, resume recording. Okay, let's do it again. Okay. So we do the varsoc to choose the lag order, in this case, 2. So we chose the lag order for the variable itself, but we haven't chosen the lag order for the moving average. So to get that, we just run and we compare the AIC and BIC. We want that to be low. Okay. So the first model we estimated was AR2, MA1. right? So we're going to try AR2MA2 to see what happens. Okay. AR2MA2, estimate that, and that's your result. You can, interpret the coefficients as we typically do, as always. But then we can check the IC here. So 2618, 2639 did not improve. Okay, so we want the criteria to be low. So it turns out that the first model, the AIC and BIC, is actually lower than the second model. So we're going to use the first model, right? 2616 versus 2618. So we can use the first model, right? The first model here. Okay. So that's our model, and we're going to do predict gold hat. Okay. That's going to give us the prediction from that model. Let's plot our gold and gold hat. Okay, so we can take a look at the gold is actually the blue, and the gold hat is the red. Okay? So our model here is pretty close to the actual data. In fact, it's very close. But the problem is we seem to uh, lag behind the actual data, right? You can see that the red line, which is our prediction, tends to hit the target after, the actual data actually taking place. So yeah, but anyway, you can see it's pretty good, right? We can compute the errors. Predict gold resid, and this is gonna give us the gold prediction and the error. Okay. So the first day we are off by negative 500. The next week we over predicted by 40. Under predict, over predict. Okay. So let's plot that. How does our error look over time? Right? So in this case, seems like our error of prediction is pretty steady, pretty close to zero, right? Except that for the weeks after week 160 here, our error starts to get wider and wider. So maybe that's time to update the model, or it tells us that the model in this period does not work with the next period, right? So a lot of time series work is, it's data driven, right? So we just kind of there's not much theory behind, the theory is well known, but in terms of fitting the model, we kind of have to choose, try uh, which one works, go with that. In this case, we might have to change model once we reach the later weeks. Okay. So that's that. You can give that a try uh, on your own. I think I'll give this for you as a in class exercise. Okay, let's say we have this result from the linear regression estimate, statistical significance. So there's statistical evidence that, as soy increases, gold price falls. Statistical evidence, but is that causal? So far, we can only say that this is statistical correlation, right? So one of the ways that this number can be wrong is that the variables are non-stationary, right? So let's test if they are not stationary or not, right? We use the Fuller. It won't let me do more than one. So let's do gold. And we find that gold is non-stationary. So we are pretty sure that this number is not good, not correct, right? But just for completion, let's test soy as well. The Fuller soy, not significant, right? So soy is also non-stationary. So both of these are non-stationary. How do we then get the estimate that would uh, at least be closer to a causal relation? Right? This is spurious through non-stationarity. So the first step is to get rid of stationarity. Okay. So let's see the most common way to get rid of stationarity is first difference. Okay, first difference. So we're going to try that. So we're going to test for gold close, but we're going to test not for the value itself, but for the first difference. The way we do that is put D dot in front of gold close and test that instead. Okay. Oh, look at that. Stationary. Okay. So let's do the same for soy. In other words, we're looking at different stationarity. Soy, same thing. Soy is also stationary when you take the first difference. So the next step is then to estimate the model with the difference instead. Okay. Right. So instead of soy predicting gold price, we're using the change in soy price to predict the change in gold price. Enter. Okay. All right. Now, as in the previous case, you know the change of soy price today. You want to predict the change in gold price tomorrow, right? You don't want to know it today and predict today. That's already known. So we're going to use the lag of soy difference as our predictor. Okay. Now we have a good model here. We observe the change in soy price today. We can predict the change in gold price next week. Okay. So that's our model. Let's see how good our model is using different criteria. We can try the error. We can try um, the plot. Right? So predict the gold hat. Okay, so we're going to predict the change in gold price and call that variable the gold hat. Okay, okay. And then we're going to plot those two. Okay. Now our model is right in the middle here, the blue, but the change in gold price is actually the red line. So how good is our model here? Uh, maybe not that good. Doesn't fit that well, right? Uh, Especially for later weeks, the similar story as before, that the error gets larger and larger. So our change in gold price is the red line, but our predicted change is the blue line. We have some good sign here in that we tend to be timely in terms of our prediction. The blue says, hey, we predict that gold is going to fall next week, right? But then it falls the following week, right? So we predict that gold is going to fall. It actually falls, but the magnitude is quite different from the real thing, right? So there's some glimmer of hope here. Some where, right? We predicted to go down. It was going down. Right? So how good though is this model? We can see the error. Let's check the error here. They're all drawings. Let's check the error. Annotate. Predict error as residual. Okay. And then let's plot the TS line. Our prediction error. Hmm. Went from negative 100 to 100. This is the actual price change that we predict wrong. Some weeks we're off by 100 on the lower end. Some weeks we're off by 100 on the higher end, right? And some indication that in later weeks, our error tends to get larger. Okay. So yeah, AR, this is a DL. And of course, yeah, so we just learned that we're going to use first difference if it's non-stationary, right? And we get more reliable. Reliable doesn't mean good prediction quality, but reliable means the interpretation is right, right? At least we're not looking at their correlation based on just stationarity, non-stationarity, but the correlation happens, you know, because of something else, right? I mean, of course, that's a topic for investigation, but at least we know that it's not caused just by the nature of the data itself. Okay. All right. Uh, should be that.